Today is Hao Peng. You're a master's student,
Master
right?
student. I will graduate this May.
Graduating in 3 days, and this is going to be presented at NetSci in this couple weeks, right?
In June.
In June. Okay. So thanks so much. Looking forward to hearing about this.
Okay, thanks. Thanks everyone for coming. Today I'm going to talk about a quantitative framework for revealing disciplinary organizations of science. It's a joint work with YY and Chinka. So let's get started. And science is a quite large, complex system. And in this system, we publish or communicate knowledge in academic journals and conferences. But it seems quite normal to you, but actually it took us thousands of years to the currently adopted format. So we went from writing by hand to debating, printing by machines, all the way to periodical journals. And now, academic journals are categorized by disciplines, like for PR, for physics, we have PRE, PRA, PRB, and they are also can be organized by research topics. You can organize by the research topics. For example, KDD, ICWS, and they all publish papers related to social networks. And now science flourishes. A rough estimation, we have more than 25,000 scientific venues. They are very important because not only because they are aggregators of scientific discoveries or our communication media, but also because scientists like you guys, you publish, you monitor, read in these scientific venues. And in my following talk, I will use this phrase, scientific venues, referring to academic journals and conferences, so include these two things. And with so many venues, can we create a map of these scientific venues such that we can systematically analyze them? And in particular, we want to answer questions like what are the relationships, how to quantitatively measure them, like the similarity between PS and science, and how can they organize on different disciplinary scales? Which one is first? And can we detect meaningful scientific dimensions across many, such that these dimensions or axes applies across many disciplines and also many research topics? One possible solution is to find numerical representation of all these venues, but there are many available representation learning techniques as far as you know. And in this work, we are inspired by word-to-web because it's efficient and scalable, easy to train. All right, word-to-web, let me introduce word-to-web a little bit. It's a language model designed by computational linguistics. The idea is consider a document as a sequence of natural language words, and you can feed large collections of such documents into word-to-web model, and you will learn vector representation or numerical representation of each individual words in a high-dimensional space. And in the end, words in similar context will have similar vector representation. For example, for the women and queen, their vector representation appears to be very similar. And based on a word-to-web, they detect the semantic axis in natural language, like this one, country to capital axis. So all these word pairs and country capital pairs, they follow or align in this direction. If you move around, given an arbitrary country word, you can detect its capital corresponding capital city just based on arithmetic operation between their vectors. This is very useful. And how can we apply this similar idea to learn vector representation of scientific venues? And in this work, we propose a model or framework, which we call hierarchical word-to-vec, just to learn vector representation from a paper citation network. But now a bunch of questions like what are the words, what are the sequence of these unique values and sentences, how to generate a large collection of such corpus. Okay. Our framework seems to solve this problem in a straightforward way. This is a bunch of papers, and it forms a paper citation network. We generate large volume of value sequences use random walk strategy. So to generate each sequence, we first randomly select the paper node, and then we follow the citations, each step randomly until we arrive at a dead end, which means there's no citations for that paper, so it will end. And for each generated paper sequence, we replace it to its values where each paper is published. We consider this value sequence as a sentence, and then we train word-to-vec model on this generated large corpus, such that it will give us a vector representation of each of these scientific values. So we apply our framework to Microsoft Academic Graph, which is an open large dataset, science of the science dataset, and we learned about 20,000 scientific values. But one thing to notice is that in Microsoft Academic Graph dataset, they don't have any discipline information. For science, which discipline is it? And that information is missing, but luckily we find another dataset called UCSD Map of Science. They basically have discipline category information for around 25K academic journals, but only for journals, no conference. And our model, we learn 20K value vectors, including both journals and conferences, and we take the intersection between these two datasets, and in the end, we matched 12,870 journals. Each has discipline category and value vectors. And we apply a t-SNE, which is a dimension reduction technique, on this matched dataset. We obtained a map of science in 2D space. So in this map, each dot represents a journal, and its color represents the discipline category in UCSD map. Before we further explore, let's validate our model first. So for PNAS, based on cosine similarity, we find it's mostly similar journals to PNAS, such as PLOS Biology, Nature, and Science. They are all located in close proximity to PNAS, which makes sense to us because they are very similar in topic-wise and research topic-wise. Well, it's apparently that there are clusterings between the 13 disciplines, but further examination revealed many complex structures like misclassifying and microclustering and mixing. The three insets highlight such examples. This bottom left one, is a microcluster of archaeological journals, which are previously classified as Earth Science in Map of Science dataset. The category information is taken from UCSD map, the previous work, but it's located close to social science in our map. And another example, the bottom right one, is a bunch of magnetic resonance image journals, which are classified as either medical specialty or brain research in the previous work. And the last example is a bunch of parasites-related journals, but it span across many disciplines, including biology, infectious diseases, chemistry, and even social science, like the Eco Health Net Journal is previously classified as social science. So our map seems interesting and useful. Can we also identify meaningful scientific dimensions, like the one we showed before in natural language? Yes, we detected two axes, biological and physical axes. To obtain this figure, we manually selected general pairs in two disciplines and project them on the 2D space by applying PCA on their value vectors. And we can see that this direction applies across many research topics. So this one, like research matters, current opinion. Biological research, not biology, it's just technological research, and also mathematical, like this one, PRE, mathematical research, chemical related research, and also theoretical research. And we also detected experimental to theoretical axis, which means we also find that this axis applies across all 13 disciplines. We use the same way to select these pairs and project them. For example, this is in computer science. This axis is in psychology and infectious diseases, medicine. Okay. Back to our previous question, can we quantitatively measure them on various disciplines? Before we proceed, let me introduce some funny things. This is PhD comics showing the disciplines ranked by their scientific purity, which is a very funny story. Many researchers, including me, disagree. It's just a joke. Yeah, on the top is mathematics and physics. Many people, including me, disagree. However, it seems somehow correct based on our quantitative analysis. Using these value vectors from left to right. Let me introduce this figure first. Each vertical line represents a journal, and we first find the center vector between the center vector for all sociological journals and the center vector for all mathematical journals. Then we build a direction between the center vector. For each journal, we measure its purity value as the cosine similarity between the direction vector and that value vector. So we can project them on this spectrum. From left to right, sociology, psychology, biology, and chemistry, physics, mathematics. You may argue that I'm cheating because I annotated these manually or randomly select these pairs, but this is a global or general ranking, ranked by their mean purity value for all the journals in each discipline, 13 disciplines in total. So math and physics here, and chemistry, biology, social science. And using a similar technique or using the same method, we also build a spectrum between natural and social science. We group both journals into two categories. Social science and natural science, we find the center vector, build a direction, and measure the cosine similarity, and project them on this spectrum. Interestingly, we find that many computer science conferences, ICWSM, ACL, TDD, they are somehow on the social science side. And more importantly, ICWSM is the most social one among these conferences. We also annotate some journals. Again, this is the general ranking for all the disciplines on this spectrum. And actually, medical related research are very natural. And humanity, brain research comes to chemistry, biology, engineering. So this is our previous, the current work. And in summary, we present a framework. It's useful, efficient, and robust. And we can use it for value recommendation in varying discipline categories. And we also detect the disciplinary organizations on different spectrum scales, and also find the meaningful semantic dimensions or directions. So thanks for coming, and the project is still going on. We are eager to explore other research questions. And any questions? Oh, I can go back to the previous slides. Yeah. Okay.
I didn't quite get like your example of purity and how this
Yeah.
was derived with the spectrum.
Yes.
How does this?
Okay.
Where does this come from? I didn't get that.
So here's the map for or the match 12,870 journals. It's just journals because UCSD map they don't have information for conference.
Right.
And we only match this number of journals. Then because people argue that in this comics, they argue this is mathematics and the most pure science.
Right.
Now we have all the journals in this category, right?
Mm-hmm.
And we find the center vector, just averaging them for all the journals in this discipline. We did the same thing for the sociological journals.
Mm-hmm.
Then a vector A minus vector B is a direction vector. We call it as a direction vector. After that, we can measure for each of the value vector their cosine similarity, right, between them.
Mm-hmm.
And cosine similarity is between -1 to 1. So that cosine similarity we regard it as the scientific purity on this axis, on this direction. And there are basically 12,879 here. And each color represents the discipline category. It's taken from the UCSD map of science data. Does it answer your question?
Yeah, thanks. I guess the notion of purity, like, okay, so you can cluster them according to the discipline, you can measure the distance, and then you can...
Yeah, this is for fun, because we don't know for sure the comics. And
But wouldn't that just mean that they're like tightly clustered?
So the key point is, as KCD, they line them up, right?
Okay.
From math physics to like social science.
Uh-huh.
The question was, do we really have that kind of direction in the vector space?
Okay.
And we tried like math physics as a group, one endpoint, and social science and humanities as another endpoint.
Oh.
And there's a direction going from social science to math physics.
Okay.
And then you project every other disciplines onto this direction, and you get the same kind of alignment with the
Okay.
So
yes.
it's like
On this map, you can also this is math and physics here, and humanity and social science here. So you can imagine that the direction goes from here to here.
Right.
Then we can project them.
Yes, I think it's interesting that you actually can see one like direction in the space
Yeah.
that represents something kind of intuitive.
Okay.
On this slide, so the next one where you zoomed up, you zoomed up into the lower left corner of this one.
This left.
Yeah, and then so the next step you actually zoomed up in there, I think.
Yes, you want to zoom in?
Yeah, let's zoom in. Enhance, please.
This picture is too large.
Reminds me of that. The streets. Have you seen the streets executed? Yeah. what did they say? They say, oh, this glue for larger beans? I don't know. It's one of my favorite movies. Okay, anyway. Maybe I heard wrong. Did you say something about earth science here? I thought you said something about earth science.
Yes,
journals.
earth science.
But is archaeology, is that?
So can you first zoom out maybe? Go
Oh,
back
zoom
one
out,
slide.
okay.
So earth science is at the top.
Okay,
At the
okay.
top.
Yes, earth science.
But there are also a small cluster of earth science journals right there and within the social science.
But are those the archaeology?
Yeah.
And, okay.
Yeah.
So archaeology counts as earth science?
According to previous
According to
categories.
previous categories. Okay.
But this map kind of shows that it may not
Yeah.
really earth
Yes.
science.
It's learned from the citations. So papers
I
published in these journals, they cite sociological papers.
So
very
the
frequent.
Google or whatever data set you said you were using labels archaeology as an earth science? Is
No.
that what you mean?
So
So
there's
for-
a previous categorization,
Oh,
manual category
UCSD.
of journals.
Okay, I see.
And this map is from the data, citation map of data.
I see.
And it shows that they are very different from other earth science journals in terms of citation pattern.
But they defined archaeology
As
to
earth
be an earth
science.
science. Okay.
As earth science.
And then can you go to the slide where you were showing those different dimensions? It was a little bit earlier, I think. It was,
Dimensions.
yeah, they were like pairs of dimensions, or maybe a little later. Yeah. Can you explain what you did here again?
So we manually selected general pairs in biology and physical disciplines. And then we use PCA to project them. PCA under this set of value vectors,
Okay.
project them on this 2D space. And we select them based on the similar research topics. For example, Journal of Applied Physics, experimental or applied. They are both doing experimental research. Theoretical research, theoretical physics, theoretical biology,
Okay.
and nanotechnologies in physics and biotechnologies in biology.
So this slide is showing me the pairs that you manually chose.
Yes.
Okay. Is there any significance to the way they're laid out in the slide? Is that showing me the result of
The direction.
yeah?
The direction.
So this is analog to like the example with word vector where country to capital
Country to capital.
words always had the same direction.
Oh, I see.
So this is basically the vector of one thing minus the other, right? And they all have the same direction and length, or roughly.
Well, we can manage, but we just project.
yeah,
Then
right. Yeah.
we connect. We draw a line between the 2 points.
In
Okay.
this case, we don't have the answer,
Yes, we don't.
so it's kind of shaky
Yeah.
because we need to find
No,
manually.
but that's fine. Yeah. But you created this projection, and then you manually selected some pairs, and you connected those pairs together. Connected those pairs together.
Yes, because it's not like in the country to capital we have ground truth relationship,
Sure. Okay.
and this is actually very hard to navigate through 20K.
So the
journals.
projection didn't know about the
No,
pairs.
they just use the vectors,
Yeah.
then
Yeah.
project.
The projection is after pulling all the pairs.
Oh yeah.
Oh, it is.
Yeah.
After we select, we just project based on these vectors, not the whole set.
So the projection does know which pairs you've selected.
So, given these pairs, projection try to find the most largest variance axis.
Okay.
That's this parallel, and the other axis is across different.
And
Yes.
so the interesting part here is looking top to bottom as opposed to left to right. Is that right? Because left to
No.
right, we would expect them to be separated because the projection knows that they're supposed to be separated.
Well, the interesting part is they are roughly parallel.
Yeah, the parallel. So now,
Right.
given another journal on one discipline, we follow this direction, we may find a corresponding journal in the physics discipline.
Okay.
And we also did this, use the same method to find an experimental to theoretical relations. So this is each pair is in the same discipline. It's not cross two disciplines like the previous one. This is
Right.
each pair in the same discipline, but it's one is experimental research journal, and the other one is a theoretical journal. After we manually select this pair, then we project them using PCA, and they roughly follow the same direction. The results is not so good as the previous one. For example, this one. These are in infectious diseases, theoretical research, and experimental research.
So if you see what do you think is the purest science?
No, our main point is the one after the purity,
Computer
the
science,
spectrum
clearly.
between natural and social science.
Network science at this. When he gives this in June.
So I agree with this picture. If you read a lot of papers in ICWS and DAP,
But
if you
here one of the biases is there are more journals in bio-related medical
Yeah.
stuff. So it's essentially medical and a little bit of physical science versus social science. So like physics is not the extreme, but somewhere biology is the extreme. The other one is from less physics to social science, so that's why biology is better.
So this is really cool. Do you have? Is there some like implication here for something yet? Like, does this tell me where I should publish, or which field I should join, or who I should talk to, or who I should avoid, or anything like that?
yeah, the next step we're trying to predict for basic research and applied research, which kind will produce significant work.
I mean,
Who we should fund.
Basic, yes,
I mean the
basic research.
most immediate thing you can do is, okay, given what you have published, here are other really similar places.
That you might want to check out.
Or if you want to move toward more biology, you can add vector toward biology and see what kind of other journals you have. So yeah, that kind of
Yeah,
vector
that's neat.
arithmetic can be interesting.
Yeah.
And the thing is now, given this embedding, everything can be point cloud, like author, paper, journal, whatever. And then you can measure how spread out, or where is the center,
Right.
etc. So
Quantifying this.
yeah.
Yes, quantitatively measure things.
All right. We're about out of
You have
time.
another question?
But can you go to the PCA?
This one?
Yeah. So the two dimensions are the two dimensions you identified by PCA.
Yes.
So in the second one, the experimental theoretical axis has a component on the dimension? Is that
I mean two component. Then so we removed the x-axis and y-axis.
so as you go towards like experimental journals, you also kind of move in the x dimension?
Yeah, but that direction doesn't mean anything. It
Yes.
just means given this point, what's the large size?
So the x is not the PC domain.
I mean, the first principal axis,
Yeah.
but that itself doesn't mean anything. It just captures, given this data point, which direction is the largest. That's not necessarily mean something.
Yes, the relative positions doesn't mean anything. We just want to say that there is a parallel direction between these. That their positions are different because if you look at the big map, and they are projected everywhere.
Sorry, I have to go. But
Oh, yes.
you should continue. Thank
Yeah.
you so much.
Thank you.
This is really good. Thank you.
When you do the random walks to generate the sequences,
Yes.
does the starting point have an effect on this?
It's hard to say because if you randomly select the paper, recently paper, the sequence might be longer, right? You follow the citations. If you first select a very old paper, like 50 years ago, the sequence may just includes 2 or 3 values. But the our framework we generated large collection of such sequences, so it might be solved that problem. And also, if we go back to natural language, the corpus, and this we are monitoring or simulating the way that how we write sentences, because we can write short sentence, we can also write a very long sentence, and that's the way they use to train word to vec. Yeah. Any other questions?
Thanks.
Yeah.
Really
Thank
cool.
you.
Sure.